Okay. Okay, so I'll wait for 2 minutes for everyone to join and then we'll start the lecture. Okay, I suppose most of the students have joined. So any specific reason that why very only these many students have joined today? All right, let me start with today's lecture. Let me share the screen. Okay. Okay, I suppose in the previous lecture, we had started with the introduction to multi-layer perceptron. Okay. So before we proceed with multi-layer perceptron, just a brief introduction. So we started with the discussion of perceptron, which is of something of this form. Okay, the perceptron is something of this form. So here in the PPT, if you can see, we were passing in certain inputs with a bias term, and there were certain weights assigned to that connection, and there was a summation of weights and inputs, the weighted sum of input, which was passed through an activation function to create an output y, right? But in the case of perceptron, the issue with us was mostly binary classification was easily performed with the help of perceptron. So we came across an issue in this perceptron theory, which was of XOR problem. Okay, XOR problem that we came across in the last lecture. We discussed that whenever we are trying to perform the train the perceptron model with the XOR for an XOR problem, it was not very much possible with a single layer perceptron. Okay, with a single layer perceptron, it was not possible to train for an XOR problem. So that's why we got an introduction to multi-layer perceptron. Okay, so just a brief, if you. Okay. So in this case, if you see the XOR table is of something of this form, X1, X2 is the input that we are going to pass into the model, and Y is the expected output. That is the actual output of the model, actual output that is expected from the model. But whenever we are trying to train this particular perceptron, single layer perceptron with this particular data set, it will not be linearly separable. The data is not linearly separable, hence this cannot be solved with the help of a single layer perceptron. So we came across a we also discussed that we can solve this particular problem with the help of a non-linearity. Okay, by introducing non-linearity into your perceptron model. So far in the perceptron was dealing with linear kind of data in which it was easier. Okay, we can easily divide the data, linearly separable data, we can easily perform using a single layer perceptron. But when there is a non-linearity introduced into your data set, there is a need of multi-layer perceptron. So we also saw in the previous lecture that we solved the XOR problem by introducing an hidden layer into the model. For example, one of the gates that we used is OR in one of the hidden layer, hidden unit, and another gate that we used is NAND, and passed X1 and X2 into the model, and then passed it to an XOR, perform the XOR of the same, right? So this is how we perform the XOR. That is, we introduced a hidden layer to satisfy our non-linearity. Okay, to satisfy our non-linearity, we introduced a hidden layer. So that is how we got introduced to multi-layer perceptron. So what is the basic diagram, basic architecture of a multi-layer perceptron is of this form. So if you see in the first slide that is present with you, this is the basic architecture of a multi-layer perceptron in which you are given certain first layer that is present as input layer. The next layers, the following layers after the input layer will be your hidden layer. There may be one hidden layer or more than one hidden layer present in your multi-layer perceptron. But for a easier version, right now we'll be discussing with a single layer, a single hidden layer perceptron. Okay, and all the input, all the neurons that are present, all the perceptrons that are present in your multi-layer perceptron will be connected to each other. Hence, this is also known as a dense kind of architecture where all the neurons will be connected to each other, and the last layer will be your output layer. So in this, all the neurons that are present in your hidden layer as well as the output layer, these are actually perceptrons. Actually, these are, if you see, they are actually your perceptrons. So what will happen in the first hidden layer? So first process that will be happening in the case of multi-layer perceptron will be, so up to this everyone is clear why we got introduced to multi-layer perceptron and what is the basic architecture? Up to this everyone is clear? Okay. So if you have any doubt, you may ask in the chat box, or please unmute yourself and ask so that we can discuss it properly. Do not hesitate to ask any questions in the lecture, fine? So that's how we got introduced to multi-layer perceptron in order to satisfy our non-linearity in our data set. Okay, so there will be a certain data set which will be having a lot of non-linearity. That's why we got introduced to multi-layer perceptron. So the structure of multi-layer perceptron will be, there will be an input layer, there will be an input layer, there will be a hidden layer, and following the hidden layer, there will be an output layer. Okay, and all the neurons that are present in the multi-layer perceptron. Actually, the multi-layer perceptron is formed from a different perceptron itself, single layer perceptron itself, right? So these are perceptron will also contain certain activation function. Okay, so we remember what was the activation function, what was the activation as an output in order to generate an output in a single layer perceptron. Okay, if you recall, when we discussed about a single layer perceptron, what was the function that we used to generate the output? We actually use a threshold based activation function, if you recall, right? So for example, if our summation of xi Wi was greater than or equals to 0, we assume that the output of the single layer perceptron will be 1. And if the value of this, if the summation weighted sum of the inputs is less than 0, then our output was 0. So this kind of threshold based activation function we had used in the case of a single layer perceptron. In this case also, in the case of multi-layer perceptron also, all the neurons that are present in your hidden layer as well as the output layer will contain certain activation function. Okay, activation functions will be contained in this multi-layer perceptron with all the neurons that are present in your multi-layer perceptron. So for example, in the hidden layer, you may use certain activation function that we have already discussed. For example, sigmoid. Okay, if you recall, in the case of logistic regression, we had discussed the sigmoid based activation function, in which what it was doing is it was actually squashing your data between 0 and 1. Okay, it was squashing your data between 0 and 1. Similarly, we had also discussed about softmax activation function, if you recall, in which we were doing the summation of e raised to z1 upon summation of all the e raised to z. Okay, this kind of activation function, softmax activation function was also there. Similarly, there are other activation functions as well. For example, tan h is an activation function that we have. In some advanced neural network structure, if you will implement neural network structures, in that ReLU is an activation function. Okay, these are activation functions we can use in the case of hidden layer as well as output layer. But can you tell me, for example, let us define. So for example, whenever we have a regression based problem, okay, so first of all, if we are solving a regression based problem in our multi-layer perceptron, through our multi-layer perceptron, so we'll in the output layer, we'll be using a linear activation function. Okay, normal linear activation function will be using, where yk, your output yk will be equals to summation of xi w1. Okay, normal. In the case of, if you recall, linear regression function, what was the hypothesis function that we had used, which was h of theta is equals to theta transpose x. Okay, in the case of classification based problems, if we have the activation function that can be used in the output layer, right now I'm talking specifically about the output layer, can be of sigmoid or softmax. Okay, you may use sigmoid or softmax activation function in the output whenever you have to generate a classification, whenever you are solving a classification based problem. Now let us talk about hidden layer. Okay, so now we have certain hidden layers. We have introduced hidden layer in our multi-layer perceptron in order to solve the non-linearity problem. Okay, the non-linearity problem that we were facing in the case of a single layer perceptron. We were not able to satisfy the XOR problem. We were not able to solve the XOR problem using a single layer perceptron. That's why we introduced a multi-layer perceptron with hidden layers included in it. Okay, hidden layers included in it specifically to learn the non-linearity. Okay, to learn the non-linearity and solve those problems which contain non-linearity amongst the data set. So can you tell me that what kind of activation function could be used, okay, out of all the activation functions so far introduced? Could you tell me that what kind of activation could be used in the case of a hidden layer? Can you tell me what can and what cannot be used in the hidden layer? Any idea or any guess that you can make? Okay, so my question is clear to everyone. Is it clear? Okay. Okay, see, what I'm talking is, so far we discussed about the output layer. Okay, we all discussed that what are the activation functions in the case of classification and in case of regression. Okay, these are the activation function, linear and sigmoid and softmax activation function you may use. And we have introduced the hidden layer specifically to solve our non-linearity problem. Okay, non-linearity problem that we were facing in the case of XOR problem. Right. So what are I'm just asking that what is the possible activation function that you may use or cannot use in the case of hidden layer? Any guess that you can make? So we can, yes, tan h is an activation function we can use in the case of, yes, right, sigmoid is an activation function, right, Priya? And Janil, those of you have answered, Keval. So sigmoid is an activation function that we can use in the case of hidden layer. But what is an activation function that we cannot use? Any idea? Any guess that you can make? Yes. Right now we have not introduced ReLU. So just tell me amongst the sigmoid, softmax, and linear. Yes, linear is a one, linear, right? Linear, right? Okay. Also, we cannot use softmax as well. If you see, softmax is specifically to generate the output in the case of classification-based problem. So there is a possibility that softmax may not be used as well. But linear cannot be used. Specifically, linear cannot be used in the case of hidden layers. Is it clear why it cannot be used in the case of hidden layer? Are you clear with the idea that why it cannot be used? Yes. Okay, so since hidden layer, so for those since hidden layer is specifically introduced in order to satisfy your non-linearity problem. So when if you actually use an linear activation function, then it won't be able to learn the non-linearity amongst your data set. Your output will not have much. It will not study the non-linearity amongst the data set. That's why we cannot use a linear activation function in the case of hidden layer. Okay, is it clear? I suppose everyone is clear with this idea. Up to this, everyone is clear? Okay. Okay, shall we proceed again ahead with the next part now? Okay, so okay, why we cannot use softmax? So see, softmax is mostly, if you study, then softmax will mostly be used in the output layer itself. So if you recall, in the case of softmax, what we were doing is we were doing multi-class classification. Okay, sorry, multi-class classification in which we had more than two classes. Okay, more than two classes were present in it, and we were specifically using it in the output layer, to generate the probabilities for different classes that we have. So that's why it cannot be, most probably it won't be able to give a good result in the case of hidden layer. If you use in the hidden layer, it won't be able to give a good result. So mostly softmax is always used in the case of output layer itself, because we want to create multiple probabilities for different classes, right? Are you clear with this, Priyank? Yes or no? Okay. What about others are also clear, I suppose, right? Okay. So now let us proceed with our discussion. So we have introduced our activation function, which we can use in the case of hidden layer and output layer. Now, so for example, now what is the process that is happening in the case of multi-layer perceptron? What is the process that is happening in the case of multi-layer perceptron? So there are two main processes that will be happening. First will be forward pass, and the next will be backward pass. Okay, forward pass and backward pass. These are the two things that will be happening in the case of multi-layer perceptron. So forward pass, if you relate this forward pass with the case of linear regression, just an example, through an example I'm trying to explain. So if you relate this with the case of linear regression, then what is forward pass? Forward pass is simply you are passing your inputs, you are calculating the activation. For example, these are the inputs that you have, x1, x2 are the inputs that you have. You will be passing the inputs to the following layers. For example, you will be passing it to the hidden layer. The hidden layer will perform certain calculation, that is, it will also have a sigmoid activation function that is present in the hidden layer, which will perform certain process on the input, which input to the hidden layer will be in the form of summation of xi wi. So there will be weight assigned to each of this connection. So for example, w1 is the weight assigned to this connection, w2, w3, and w4. These are the four weights assigned to all the connections that we have, where we are passing all the inputs to all the neurons that are present in the hidden layer. So for example, there are 4 neurons present in the hidden layer, then the input x1 will be passed to all the neurons that are present in the hidden layer. Since we are talking about a dense connection we are talking about, where all the layers, all the neurons present in one layer will be connected to all the neurons present in the successive layers or preceding layers, right? So we are talking about a dense space connection. So in this form of connection will be there. So what will happen in the hidden layer? Hidden layer will perform certain calculation. For example, the weighted sum of the inputs and the weighted sum of the inputs will be passed to the hidden layer. The hidden layer will contain an activation function. It will calculate the output. For example, H1 is the output of the first hidden layer and H2 is the output of second layer, hidden layer. This hidden layer output will then will be passed to next hidden layer. For example, if we have a 2 hidden layer, suppose we can have more than one hidden layer in your multi-layer perceptron. So right now I'm talking about just one hidden layer. For example, in this particular diagram, I'm talking about just one hidden layer. Then this hidden layer input will be passed to the output layer. So this is your output layer that is present, which will also be a weighted sum of this output from the hidden layer as well as the weight assigned to this connection. So for example, W1 is the weight assigned to this connection and W2 is the weight assigned to this connection. And then this weight summation of W1 H1 and so on plus W2 H2 plus bias term. So I forgot to introduce a bias term here. So there is a bias also. This sum will be passed to the output layer, and output layer will generate the predicted output of the model. Okay, predicted output of the model will be generated to the multi-layer perceptron. So this whole process that is happening, this whole process is called forward pass. This whole process is called forward pass, that we are passing the input through the hidden layers that are present in your multi-layer perceptron and generating an output through the multi-layer perceptron, generating an output, and then we'll calculate the loss associated with the multi-layer perceptron. So for example, in the case of linear regression also, if you recall, we were calculating the loss associated, what was the cost of this function, what was the cost that is generated by using a particular weights, the particular value of the parameters. Then later, what was happening was we were calculating the cost that was generated and later updating the weights in order to minimize the cost function, right? So it's the same process will be done in the case of multi-layer perceptron as well, right? And there was one question that was asked in the previous lecture by Keval, I guess, that why do we need to use what is the specific need to use a differentiable activation function? So I suppose that everybody is clear that why we need to use a differentiable activation function in the case of multi-layer perceptron. Can you tell me why do we need? So for example, up to this everyone is clear, right, that we'll be performing a forward pass. Then the next process will be to calculate the cost associated with the perceptron, multi-layer perceptron, and then to adjust the weights of all the model, adjust the weight associated with all the connection such that the cost generated, that the loss that is minimum, such that we minimize the loss associated with the output, right? So that was the case in the case of linear regression as well, and that is what we'll be doing in the case of the multi-layer perceptron as well. And I had specifically mentioned that all the activation functions that we'll be using in the case of multi-layer perceptron must be differentiable. Okay, must be differentiable. So if you see, there is another activation function that we had used in the case of a single layer perceptron, which was a threshold based activation function, which was summation of xi wi is greater than equals to 0. Then it will output as 0, output as 1, otherwise it will output as 0. But we cannot use this kind of activation function in the case of multi-layer perceptron. We have to specifically use a differentiable activation function and a continuous activation function, because we will be calculating gradients. Yes, we will be calculating gradients. Are you clear with this? Why will we be calculating gradients? Why will we be calculating gradients? Because we are what we are trying to do. We are trying to update the weight associated. Yes, we are trying to minimize the loss and we are trying to update the weight associated with all the connections. That's why we need to perform the gradient. If you recall the gradient descent function, gradient descent algorithm that we had discussed in the case of linear regression as well as in the case of logistic regression. What was the case? We were trying to identify that what was the changes in, by calculating the derivative of the loss with respect to the parameters. We were trying to identify that if we make a certain change in the weight, then what is the possible change in the loss. Okay, that is what we were doing. We were trying to update the values of parameters associated with all the with the entire data set by calculating the gradients associated with the this model, gradient associated with linear regression model and gradient associated with logistic regression model. That is what we'll be doing in the case of multi-layer perceptron as well, which will be your backward pass. Okay, which will be your backward pass, where you'll be trying to update the weight associated with all the connections so as to minimize your loss. Okay, is this clear, everyone? Both the forward pass and backward pass, and why we are using a differentiable activation function. Is this everyone is clear with this or not? Let me know. Okay, I'll repeat the backward pass. Yes. Okay, so I was talking about for in the forward pass, what we are doing, we are calculating the value of the output. That is what we are doing in the case of forward pass. Now, when we are talking about in the case of backward pass, that I'm just introducing the point of backward pass right now. So what we'll be doing in the case of linear regression, what we were doing is we were calculating the gradients. We were in order to update the values of parameters. The main idea was to minimize the loss by updating the values of parameters. Okay, minimize the loss by updating the values of parameters. That is what we were doing in the case of linear regression. So in this case also, in this case, multi-layer perceptron also will be calculating certain loss associated with the output. Okay, there will be certain loss associated with the output. The predicted output will be something, and there will be an actual output associated with the data set, with the input that we are passing. So now we'll be calculating the loss, and we have to minimize the loss. In order to minimize the loss, the idea is to update the values of parameters in such a way that your loss is minimized. So in order to minimize the loss, what we have to do, we have to calculate the gradients. Okay, we have to calculate the gradients associated with all the parameters, yes or no. So in this case of linear regression, if you recall, we were calculating the gradients associated with W as well as with bias. Yes or no? We were calculating the gradients associated with all the parameters that were present in a linear regression model. Similarly, in this case also, we'll be calculating the gradients associated with all the weights that we have in all the connections that we have. So we'll be calculating the gradients. That is, we are performing backward pass. So the error that is calculated at this point, error that is calculated will be propagated backwards in order to update the values of parameters. So what will be happening is we'll be propagating this error backwards. That is, we'll be propagating the error backward means we'll be trying to calculate the gradients of associated with all the layers. For example, for the output layer, we'll be calculating the gradients. That is, what is the weight update for this connection. Similarly, for hidden layer, we'll be calculating the weight, what is the updated weight for this connection, and so on, to minimize the loss. Are you clear with what we are doing in the forward pass now? Sorry, backward pass now. Is it clear now? Is everyone clear with this now? Any doubt? Okay. So, okay. So up to this, everyone is clear. So this is the two thing that we'll be doing is, first is forward pass, where we'll be calculating the output. Next will be backward pass, where we'll be propagating the error backwards in order to calculate in where our main idea is to update the values of parameters so as to minimize the loss associated with the model. Okay. Now, this you can see mathematically also if you will try to solve this particular problem. Okay. So this particular point that we discussed, the propagating the error backwards, is known as backpropagation algorithm. Okay, backpropagation algorithm, in which we are trying to calculate, in which we are trying to update the values of parameters by propagating the errors backward so as to minimize the loss associated with the multi-layer perceptron. Right. So in this, okay, now if you see in the case of output layer, so we have two layers here in which we'll be calculating, we'll be trying to update the weights associated with the model, where one is the output layer and one is the hidden layer. So if you see, that is directly, in the case of output layer, we have a directly associated error. Yes or no? We can directly calculate it. There is an error associated with the output layer, yes or no? Because we have an output in the output layer, and we haven't predicted actual output. We haven't predicted output in the output layer, and we have an actual output associated with the data set. So we have an error, direct error associated with the output layer. But this is not the case with the hidden layer. Yes or no? This is not the case with the hidden layer, because in the hidden layer, we do not have an actual output. Yes or no? Are you getting my point, what I'm trying to say? Yes? Are you trying to getting the point? Okay, so in the case of output layer, we have a direct error associated with the output layer, but this is not the case with the help of hidden layer. In the case of hidden layer, in the hidden layer, we do not have an output associated with it. So we cannot calculate error in the case of hidden layer. So what are we trying to do in this? The main idea in the case of backpropagation is to propagate the error backwards so as to calculate the error at the hidden layer as well, which we'll see in the case of using the derivation also. We'll also see through the derivation where the output layer error will be propagated backwards in the hidden layer. So that we can calculate the error associated with the hidden layer to update the weight associated with all the connection in the hidden layer. Okay. Are you getting the point, what I'm trying to say here? Yes or no? Okay. All right. So let us go through the derivation part now. So first, I will be if you directly go through the textbook, there will be a lot of notations present in the textbook which you might not get easily. So we'll go through an example. Easy and example, first example, so that in order to whenever you go through the textbook to understand the backpropagation algorithm, it will be easier to understand for you. Okay. So let us consider the error. First, we will be defining the error function associated with the multilayer perceptron. So for example, in most of the theories that you'll be seeing online as well as some other sources, the multilayer perceptron, error associated with the multilayer perceptron will be of MSC cost function, which is of the form 1 by 2 y hat minus y the whole square. So you already know about MSC cost function, but you may also use other cost function as well. For example, in the case of sigmoid activation function, in the case of binary classification, if you have a binary classification based problem, the cost function that you may use is of the form of binary cross entropy. Okay, binary cross entropy that we had discussed, if you recall, binary cross entropy. And in the case of softmax, we had directly talked about cross entropy loss. So these all can be also used, but some of the multilayer perceptron models are utilizing sigmoid along with MSE loss function as well. So it is actually whenever you are trying to implement, whenever you're doing a practical implementation of a multilayer perceptron, you may use different types of loss function along with the activation function and try to check that which of the activation function or loss function is giving me an maximum accuracy with the data set that you have. Okay, so there is no hardbound rule that MSE loss function cannot be used at this point of time with the sigmoid, but mostly you may use and you may try to analyze. Okay, for example, if whenever you're doing a practical implementation with a practical data set, for example, let us see MNIST data set. For example, MNIST data set you are trying to solve with the multilayer perceptron, you may try and analyze whether MSE loss function is giving me a good output with the sigmoid activation function. Okay, this you may try. Are you getting the point? So right now we'll be solving the backpropagation algorithm. We'll be solving the backpropagation algorithm by taking error function as MSE loss function and hypothesis function in the output as sigmoid. And we also already know that in the activation, in the hidden layer, the activation function that we'll be using is sigmoid activation function. Okay, up to this, whatever I have defined for us to proceed with the derivation part, is it clear or not? So I have defined the error function, the output hypothesis, output activation function that we'll be using, and hidden layer activation function that we'll be using. Up to this, everyone is clear? And whatever I discussed with the loss and this, is it clear to everyone? Any doubt? Okay, so let us proceed with the derivation part now. Okay, let me go through the slides. Is it visible? The slide is visible to everyone? Okay. Just take an example. Let us take an example. For example, in this particular example that I have used, I have taken a single hidden layer perceptron. For example, a multi-layer perceptron has been defined here, where I have two inputs, x1 and x2, and I have a single hidden layer that is present here, and I have an output layer that is present. And activation function that I am utilizing in both the hidden layers is of sigmoid form. Activation function that I am utilizing in the output is of sigmoid form, and the error function that I will be utilizing in this particular multi-layer perceptron is of MSE loss function. Okay, that is defined. And this is the notation that we are using. For example, the connection from x1 to the first hidden layer is w11 to the 1, that is layer 1, and w12 to 1, which is the connection from x1 to the second hidden layer, second neuron in the hidden layer. Okay, just now this one. Okay, similarly x2 to the first hidden layer neuron and x2 to second hidden layer neuron. Okay, and similarly the connection from the first hidden layer neuron to the output layer and second hidden layer neuron to the output layer. These are the notations that are present in the multi-layer perceptron that we have created for understanding. So first process that will be happening is the forward pass. So we have already discussed about the forward pass. What will be happening in the case of forward pass? In the case of hidden layer, in this particular point, hidden layer, what will be happening is we'll be calculating. For example, H1 will be the sigmoid of summation of the x1 w1, or just I'm just considering a random notation here. Just xi wi. Let us take xi wi. Summation of I is equals to 1 to n. So this will be your H1. Similarly, H2 will be similarly the summation, the sigmoid of the summation of xi wi, and so on, right? The output in the output that is generated, which is indicated by pi hat, will be sigmoid of summation I is equals to 1 to n hi and wi. Are you getting what I'm meaning through hi? Hi is the output of the hidden layer, which is being passed into the output layer. Okay, up to this every notation are clear? All the notations are clear? Yes or no? What we are doing in the forward pass? Then only we can proceed with the derivation. So just let me know, is it clear or not? Okay, so just in brief, so we have x1 and x2. We have two hidden neurons in the hidden layer, the one hidden layer that we have introduced, and one output layer, and all the activation function we have defined. H1 is the output of the hidden layer, which is the sigmoid of the summation, weighted sum of the inputs. And pi hat, that is the output generated through the output layer, is the weighted sum of the hidden layer output and the weighted sum of the hidden layer output, and sigmoid of the same. The sigmoid of the same will be your output layer. So now we'll be talking about backward pass. Okay, we'll be talking specifically about the backward pass, where we are trying to calculate the gradients in order to update the weights associated with all the connection. So for example, suppose I want to update the weight associated with this particular connection, which is wi1 w12. Okay, this specific weight I want to update. So how will I update this weight? So if you recall, in the case of linear regression, what we did, we were trying to calculate the del j by del theta 1, del j by del theta 2, and so on. That was the process that we were doing, the summation. If you recall, the gradient descent algorithm that we had used. So similarly, what we will be doing in this case, we'll be calculating del li divided by del 1 2. Yes or no? Are you getting this point? What we are trying to do? Is this clear to you or not? Yes, is this clear? Okay, sorry, L, I forgot to mention, L is your loss. By L I mean here loss. Okay, is this clear? Is this notation that I'm trying? Okay, this first thing that I'm trying to say, that in order to update the weight associated with this particular connection, okay, this particular connection, I'm trying to update the weight associated with this particular connection. What I'll try to do is I'll try to calculate this gradient value. Then if you recall, what is the weight update value in the case of linear regression? Our weight update value was something like this: theta j is equal to theta j plus alpha into del j by del theta. Yes, this was the case in the case of linear regression. Similarly, in the case of in this multi-layer perceptron also, in order to update this particular weight, we'll be calculating w1i2 new is equals to old plus alpha, which is your learning rate, into del li upon del w12. Are you getting the point? Is this clear to you or not? Yes? Okay. So now let us go through the derivation part. So if you see, we have defined, so in this case, we have defined the loss function here. Then how to calculate those gradients, that will be seen. So if you see, our loss function is pi hat minus yi. That is the loss, that is the output associated with a particular instance of a data set. And pi hat is the output that is generated through our model for a particular instance of data. Okay, that is, we have defined this loss function that is present here, which is summation over all the training samples I is equals to 1 to n. Okay. Now, let us go through the derivation where we are trying to calculate this value, which is del Li upon del W12. Okay, this is the value that we want to estimate. This is the value that you want to estimate. So if you see, do you recall the chain rule? Chain rule in the case of derivation. So if you see, if you make certain changes in W12, then it won't be directly impacting the loss. First, what we'll be doing is it will be impacting the Z value. Z value, what is the Z value if you have is summation over Wi, summation over the weights and the input. Okay, so in the case of this particular diagram, if you see, this is a Zi value that will be having. Zi will be W12 into H1. Okay, so Zi, by Zi I mean is the weighted sum of all the inputs. Just consider the weighted sum of all the inputs. So if you make certain changes in W1, that will impact the value of Z1, and Z1 value will later impact the output value, which is your pi hat, and that pi hat which is there will be impacting your loss value. Yes or no? Are you getting this chain of connection? Yes or no? Yes, is it clear? What about others? Is this chain of connection clear to everyone? Okay, I'll repeat. See, if you see in the case of what we are trying to do is by calculating the gradients, our idea is to find out if we make certain changes in the value of W12, what will be the consecutive change in the value of loss. So we are trying to, in order to calculate this derivation, in order to calculate the gradient value, okay, this gradient value that we have to first calculate the gradient value, and then we have to update the weight associated with the W12. Okay, we need to calculate the gradient. So in the gradient, we have a chain rule. We are implementing this gradient using a chain rule. Where what is happening if we are trying to update this W12, if we are trying to update this weight associated with this connection, okay, this connection, we are trying to update the weight associated with this connection, then it won't directly impact the loss. First, what will do? It will impact the Z value. Okay, Z value which is associated with this particular connection. Z value means what? The weighted sum. Weighted sum is W12 into H1. That is the Z value that will be having. So if you recall, in the case of linear regression, the Z value was theta transpose X. Okay, in the case of logistic regression, theta transpose X was the connection. But since we have only one connection here to the output from this particular neuron, the only one Z value will be W12 into H1. That will be our Z value. After the Z value will be impacting what? Your output value. So output will be pi hat. Pi hat is the output, which is actually sigmoid of Z. Okay, sigmoid of Z is your output value that you have, which will be impacted with the help of this W12, which will be impacted with the help of W12. Oh, sorry, I just missed one point. Z value will be actually summation of W12 into H1 plus W22 into H2. Okay, I suppose that is clear, right? That is clear. Is it clear to you? Z2 will be that, because actually Z is the output. Z is the output that we are generating, which will be the sum of this and this, product of weighted sum of H1 and weighted sum of H2. Okay, that is the Z value that will be having. So changes in W1 will be impacting Z value. The Z value output, the output that is generated in the output layer, will be impacting the pi hat, which is the sigmoid of Z. And later the sigmoid of Z, that is a pi hat that will be calculating, will be impacting our loss. So this is the chain rule that is implemented in this particular derivation. So if you see, del Li is directly being impacted by del Pi, and del Pi is being impacted by del Z2, and del Z2, the changes in del Z2 is being impacted by the change in W12, del W12. Okay, Z, I'll repeat. So what is Z? If you recall, in the case of linear regression that we had implemented, if you recall, so Z value was theta transpose X. Okay, theta transpose x means what? The summation of all the parameters, theta 1 x1, theta 2 x2, and so on, theta n xn. So here also the z value is what? Z value is what? The z value is the output that we are generating in this model, the output that we are generating in this multi-layer perceptron, which will be the summation, which will be the weighted sum of the inputs that is being passed into the output layer. What is the input that is being passed into the output layer? Input is actually the H1 layer output. That is the H1, that is the hidden layer one, first hidden neuron output, and the second hidden neuron output, and the weighted sum of this. So it will be W1, it will be W12 into H1 plus W22 into H2. Okay, the weighted sum of this one and weighted sum of this one will be your Z. Yes or no? Are you getting now? Is it clear? Okay. Okay, up to this, everyone is clear? This chain rule is clear to everyone? Okay. So similarly, now that we are clear with this, so this is how we'll be calculating for del Li with del 1 2. So that is the weight associated with that connection. How we'll be updating is using this particular chain rule. So we have the value of loss that we have, which is MSE loss function. So we can directly calculate the del Li by del Pi. We can directly calculate del L by del Pi because the loss function is of this form. Okay, loss function is of L is equals to 1/2 Pi hat minus Phi the whole square. So del Li upon del Pi will be 2 times Pi hat minus Yi upon 2, which will be actually Pi hat minus Yi, right? So this is clear to everyone. This must be clear. Similarly, just a minute. Similarly, del Pi upon del Z2. Okay, del Pi upon del Z2, we have Pi is equals to sigmoid of del Z2. So if you recall, what was the derivation of sigmoid? Derivation of sigmoid with respect to, if you recall, what was the sigmoid? 1 upon 1 plus e raised to minus x. 1 upon 1 plus e raised to minus x. So if the derivation of sigmoid was, the sigmoid with respect to x was sigmoid of x into 1 minus sigmoid. Okay, if you perform this derivation by yourself also, this will be the output of which will be generated by derivating the sigmoid function with respect to x. Okay, which will be actually sigmoid into 1 minus sigmoid. Okay, this is clear to everyone? Are you getting the point what I'm trying to say here? Okay, I'm not going in the how to perform the derivation. I'll leave that up to you, this particular derivation of sigmoid with respect to x. Okay, I suppose that is clear to everyone, right? So here, this particular derivation is the Pi with respect to Z2. Z2 is actually the summation of Wi Hi plus W2 H2, and Pi is actually the summation, the sigmoid of Z. Sigmoid of Z. So you can say that your Pi hat is actually 1 upon 1 plus e raised to minus Z2. Okay, this is how you can write Pi hat. Yes or no? This is how you can write Pi hat. So it will be actually Pi hat, the derivation of Pi hat with respect to del Z2 will be equals to Pi hat into 1 minus Pi hat. Okay, this will be the derivation value. Okay, right? Similarly, the last one that we have is del Z2 upon del W12, which will be actually your input value that you are passing, because the del Z2 is actually Z2, if you recall, is W12 into H1 plus W22 into H2. So with respect to W12, it will be H1 only. So your output here will be equals to H1. So this first derivation is clear to everyone or not? Any doubt so far in what we are doing? First, this derivation is for calculating the weight associated with the connection from hidden layer to the output layer. Okay. Now we'll go to the hidden layer. How to update the weight associated from the input layer to the hidden layer. That will be solving after this. But this one is clear that we are doing a chain rule to update the weight. That is the gradient associated with this particular connection. Is this clear to everyone? Shall we proceed with the next part? So if you have any doubt, just let me know. So we'll solve it right now. Okay. So this one particular, this del Li upon del W12, this particular one. Okay, all of this okay, can you tell me that from where it is up to Z, where we define Z, that is clear, up to Z is clear, right? So let us, okay, just a minute, I'll just define this particular point here. So see, what we are trying to do is del Li upon del W12. That is what we are trying to do. So which is actually, which is using the chain rule, if you see, del Li is directly being influenced by del Pi hat. Del Pi hat is directly being influenced by del Z2. And del Z2 is being influenced by del W12, where Z is equals to W12 into H1 plus W22 into H2. Okay. So now see, if you directly calculate the del Z2 upon del, Z2 upon del W12, which will be equals to H1. Yes or no? This derivation is clear, right? Now, let us calculate for del Pi hat upon del Z2, where del Pi hat, where is Pi hat? What is Pi hat? Pi hat is sigmoid of Z2. Pi hat is sigmoid of Z2. And Z2 is actually W12H1 plus W22H2. Okay. Sigmoid of Z2. So I can write Pi also, Pi hat also as 1 upon 1 plus e raised to minus Z2. This is how I can write Pi hat because it is a sigmoid of Z2. So if you know, if you perform the sigmoid function, with the help of sigmoid function, if you perform del x by, for example, if your sigmoid function is 1 upon 1 plus e raised to minus x, and if you perform the derivation of sigmoid with respect to x, then output will be equals to sigmoid into 1 minus sigmoid. That will be the output. So in this case, where Pi hat is the function that we are defining for this particular sigmoid function, the output will be equals to Pi hat into 1 minus Pi hat. Okay. That is what the output will be, right? And the first point that we have is del Li upon del Pi. Okay, del Li upon del Pi. So for that, if you recall, L is equals to 1 upon 2 summation over I is equals to 1 to n Pi hat minus Yi. Okay, so if you perform the derivation with respect to Pi hat, if you perform the derivation with respect to Pi hat, del L upon del Pi hat, which will be equals to 2 into Pi hat upon minus Yi upon 2, which is equals to Pi hat minus Yi. Okay, this is clear. All the three derivations are clear now. Is it clear now? Okay, so now this is what we are trying to do here. So the final output in the case of this particular case will be of something of this form. Let us go to the next slide. Okay, so del Li upon del L upon del W12 will be equals to this. Okay, where H1 is the output, where since Z is equals to H1 W12 plus H2 plus H2 W22. So this is H1 for that particular del Z upon del W12. Okay, H1 and Pi hat into 1 minus Pi hat and Pi hat into minus Yi. Okay, so we can say this we can call this particular term I'm calling as del Pi hat. Okay, so we have the loss associated, we have the gradient associated with del 1 2, which is equals to H1 into del Pi hat. Okay, so we have the loss, we have the gradient associated with the first weight that is associated with the hidden from the output layer to the hidden layer. Similarly, we can also calculate for del L upon del 2 yes or no? You can calculate for del L into del 2 yes or no? Can you calculate that? In the similar manner, for this particular connection also you can calculate, right? Is it clear? For the weight associated from the connection from hidden layer to the output layer, you can calculate. For the next one also, is it clear? Okay. So everyone is clear with the question that I just asked. So I just calculate the weight, the del L by del 1 2 for this particular connection. Similarly, you can calculate for this connection also for del L upon del W22. Yes or no? Which will be similar, which will be of similar form, something of similar form. Which will also be, in this case also, you will be calculating with the help of, first the W22 will be impacting your Z value, the Z value will be impacting your P value, and P value will be impacting your loss value, right? Are you getting this point? Okay. Yes, fine. Now our next point, our next target is to perform the same operation for the case of hidden layer. Okay, up to this everyone is clear, I suppose. So next, the next part that we'll be doing is for calculating the a weight update. What will be the weight update in the case of hidden layer? For hidden layer, what we'll be doing? Okay, so let us see. Right now we are running out of time. So let us just see this particular chain rule first of all, and later on the derivation we'll do in the next lecture. So so suppose, just a minute. Or let me bring that slide here so that okay, let me make the diagram again in the next. So we have x1, we have x2, and this is the h1. This is the h1 that we have sigmoid output by pi hat. Okay, and this is the weights that we are passing. So here the weight associated is W111, W121, W211, and W221, and this is W12 and W22. And here the output from this particular sigmoid will be H1, output from this particular sigmoid will be H2, and this will be Pi hat. So now, if you see, now we'll be calculating for this particular. Now our next our target is to perform the same operation that we did in the case of output layer. Now we have to calculate a weight associated with this particular hidden layer. Okay, this particular weight I want to calculate. I want to update this particular weight. Now you see, in the case of hidden layer, we already discussed there is no error associated with the help of with the hidden layer. But if you see, okay, so we already seen that how to, for example, if we have del L upon del W12, then there is a chain rule that we implemented. That since Pi will be impacting, first we saw that Wi will be impacting Z value will be impacting Pi hat value, and then it will be impacting loss value. So now in the similar case, suppose I am updating this particular weight. So can you tell me what is the chain rule that will be implemented? So W11, this particular weight will impact the output of Z1. Okay, output of Z1. This Z1 will impact the output of H1. Yes or no? This Z1 will impact the output of H1. That is the output of this particular hidden layer. This H1 output will impact the value of this particular Z2. And Z2 will impact the value of Pi hat, and Pi hat will impact the value of loss. Are you getting the chain of products that we'll be doing? Is it clear or there is a doubt? See what is, so in case of Z2, what was the output is W11, 1H1, sorry, W1H1 plus W2H2. Okay, this was Z2. Now similarly in Z1, what will be the output is summation of all this will be your Z1. Okay, this will be your Z11 value, which is just a minute, which is X1 into W111 plus X2 into W211. Okay, for this particular I'm talking about. Okay, I'm talking about this particular value. And your hypothesis H1 is equal to sigmoid of Z1. Okay, for this particular neuron I'm talking about right now. So if you see, if I'm trying to update this particular weight, how will the chain will follow? I'm updating this weight. This weight will automatically impact the Z1 value. This Z1 value will be impacting the H1 value. H1 value will have an impact on the Z2 value that I'm calculating, which is actually the product of H1 into W12 plus H2 into W22. And following the Z2, which is Pi hat will be impacted, which is the sigmoid of Z2. And then later on the loss will be impacted. Are you getting this particular chain or not? Is it clear? This chain is clear to everyone? I'll give a more clear PPT for you so that you can understand the chain properly. But right now, just what I just explained, is it clear to everyone or not? This chain, the chain of products to calculate the gradients associated with W211. Is it clear? Okay, so we'll be going through the derivation in the next lecture. In the following lecture, we'll go through the derivation. And by today itself, I'll be uploading an assignment in the classroom where you have to upload your link, your GitHub link that you have created. That you have to upload, that you have to paste or upload, whatever you may do. You may paste it, which you have to paste there, so that I'll be clear with how many of you have uploaded all the assignments in your GitHub repository. So you have to complete it up to lab 7. Okay. And so far what we discussed in today's lecture is we talked about the multi-layer perceptron introduction, and we talked about the layers that are present in the multi-layer perceptron, and also discussed a brief about the backpropagation algorithm. And we saw for the, in this particular, I'm just taking a random example and trying to explain the chain of products that will be happening. So we discussed about the output layer so far, and we have seen the chain in the case of hidden layer. Now in the next lecture we'll go to the derivation, and then we'll conclude with the actual derivation that is present in your textbook, that is present in your Tom Mitchell book, and how to understand, how to interpret that particular derivation. So you will automatically understand the derivation after you get clear with this particular part. Okay, so we'll discuss that in the upcoming lecture, and then we'll conclude with the backpropagation algorithm that is in the multi-layer perceptron. So I hope that everyone is clear with today's lecture. Still, if you have any doubts, we'll discuss further in the next lecture, so that will be clear. Okay. So I'm ending the meeting now. If you have any doubt, just let me know right now. Nobody is having any doubt right now, right? So I'm ending the meeting now. All right.